Okay, lecture 56, hypothesis testing for variance or standard deviation, the chi-square random variable. All right, well, we've been doing population for, hypothesis testing for population mean or difference of means, population proportion, or a difference of proportions. Now we're going to go on to another parameter, the standard deviation, or the variance, which if you remember is just the square of the standard deviation. All right. Well, we've done enough hypothesis testing now that you should figure out that all you really need to know is how do you calculate the test statistic for the standard deviation or the variance? And once you have that, what kind of a random variable is it? In other words, what table of values do I need to use? And speaking of table of values, we're going to be putting one up here in it to do some examples. And so ignore these little ovals that you see, these little ellipses. I'll explain what they are later, but I need them up there right now, and you'll see why in a minute. Okay, so I say the test statistic is of a type chi-square random variable. And the symbol that we use is, well, I give it right there. And I tell you, well, I'll go ahead. I guess I'll say it right here. Chi-square is n minus 1 s squared over, well, I say sigma squared, but if we're already thinking of hypothesis testing, then really we're going to talk about the value of the standard deviation under the null hypothesis. So we can write it as sigma 0 squared. I think I did that. Yes. Okay. So n is our sample size. S is our sample standard deviation. So s squared is the sample variance, and sigma naught, I just said, is the standard deviation under the assumption that the null hypothesis is true. Sigma naught squared, then, of course, is the variance under the assumption that the null hypothesis is true. Okay. Well, what does this random variable look like? What's its probability curve? Remember, along the horizontal axis, I would have like all the values that the random variable could take. And then I would have some curve over it that told me the area under that curve gives me the probability the random variable lies between whatever two values I pick. And you look at that chunk of the area, right? It's the same thing. It's just that it's a different calculation, and the curve is a little different. So what does the probability curve for a chi-square random variable look like? Looks like this. If you have, let's say, small degrees of freedom, so which again, that's 1 minus the sample size for what we're going to see. We have a curve that looks something like this. It goes up pretty sharply here and then trails off kind of gradually. If I have larger degrees of freedom, well, it takes a little while to get to its height here, but then it still trails off more gradually, kind of off that way. And it goes forever to the right, but you notice it does not go to the left past 0. This is the value of 0 here, so it doesn't have any negative values, right? And of course, look up here. That squared is going to be a positive number. That squared is going to be a positive number, so I can't have any negative numbers here. So some things to notice is that, like I said, so note here down below, I'm kind of running out of room. Note, all values of a chi-square random variable are positive. And let's see, I can maybe squeeze this other one here. The graph, the probability graph, is not symmetric. See, am I coming in here? It's not symmetric about the hump. That. It's not symmetric about the hump, even though it kind of looks like, almost like it is over here. It's not. It goes up faster here and then trails off more gradually. It's still true that total area is 1. Likewise here, area total is 1. So it stretches out, like I said, to infinity, but of course the areas out here get very tiny. The probability that a chi-square random variable is way the heck out there is going to be very small. Let's see, I think I've said pretty much all I want to say. I just want to stress it's not the normal curve by any stretch. The normal curve, the normal 0, 1 curve, of course, is centered here, and it spreads out symmetrically to infinity and to negative infinity. This thing is truncated off at 0. It goes up faster, and then it dies off. Yeah, and I guess I've already implied this, but there's a different curve, a different chi-square variable for the different numbers of degrees of freedom, and you can see that up here. For when I change the n, I'm changing the value of the random. I'm changing the value that I calculate. I'm looking at a different random variable, a different chi-square. Okay, so what we have to be able to do is figure out if we're trying to do a hypothesis test for a standard deviation or a variance. We have to compute this test statistic, and then we have to look in the right table for chi-square and figure out our areas and figure out our critical values. So what I want to do now is just 3 quick examples. So let me rub this out. And while I'm rubbing it out, I will explain that normally I have a screen right in front of me here, so I can see what I'm doing. And I can, when I'm going to put up in a minute a slide that has the chi-square table on it, and normally I would be able to see that slide right here in front, and I could find what I'm looking for in it. The screen is broken. They're trying to get it fixed, but it's broken right now. I have a very small screen off to the left, and I put the slide up, and I looked, and I really can't quite see the slide to find what I'm looking for in the chart very easily. So I've actually pre-circled the things that we're going to need, so that's why you see these circles. All right, let's look at example number 1, the next page. So we have a sample of, what does I say? Notice how the table, okay, so if you look at, you have a table, you have a textbook, or you can go online, anywhere, you can get a table for chi-square values. And the one I'm going to put up here, I just got off from online. And notice that the table gives chi-square values for given areas to the right of the particular value. So you're always looking at a right tail probability, all right? And we'll see how we can use that to do right tail, left tail, and two-tail tests. And I'm going to run you through that here right now, in fact. Okay, so the first example, we have a sample of size 12, and I want a right tail probability of 0.05. Okay, so the picture is, I would go ahead and draw this picture in, and I probably will rub it out before I actually pull the table up here, because it's going to be right in the middle of my table. But I have a sample of size 12, so my degrees of freedom are 12 minus 1, which is 11. And so, my table, or my graph looks something like that. Okay, and what I'm looking for then is this value such that I have 0.05 in the right tail. Right? That's what I'm after, is that value right there. And I will, actually I can probably, maybe I'll just leave it up. I might look kind of messy here. Let me go to the next table. We'll see if it works. The next slide here, I have a table. Yes. Okay, now, so what you want to do is you want to go down to degrees of freedom 11, right? And then up top you want to find 0.05 area to the right, which is what all the areas up top mean, to the right. So you find that, and you come right here to that value that I've circled, and it is 19.675. All right, so if you should be able to get that right there, I think is 19.675. So there's the answer, 19.675. Let me back up then, and you can see that. Okay, terrific. Let me rub that out. No, I guess I can get rid of this. Don't need that. So if I want an area to the right, I read it straight off the table. I want a low tail area, 0.05 to the right. That's what the table gives me if I look for it, no problem. Next, I have a sample of size 50, and I want a left tail probability of 0.01. So I'm looking at a sample of size 50, and I'm not going to worry how accurately I draw the graph. I know it looks something like that, and that's going to be good enough. I want now a left tail probability of 0.01. So I want, this to be 0.01, right? The left tail cuts off at 0, but I got to go a little bit out here so that I got to have a positive area of 0.01. So what do? The table doesn't give me areas of to the left. It only gives me areas to the right. So of course, I just compute this area, which is to the right, isn't it? And of course, that's 1 minus 0.01, so it's 0.99. So I go in the table and I look up 0.99 area to the right for degrees of freedom. 50 minus 1 is 49. My table doesn't do that. The one I grabbed off the web doesn't do that. I'm going to use degrees of freedom 50. So let's see. This page goes up to, what does it go up to? 23 degrees of freedom. So if I go to the next page, I took a chunk of a table. I didn't take it all. It went on and on and on. So I just here go up to, only go up to 100, but I have here 50, right? And so like I said, I'm gonna use 50 because I don't have 49. And I want to look up at the top and find where its area to the right is 0.99. And it comes to this value right here, doesn't it? 50 and 0.99 to the right, and that gives me 29.707. 29.707. Okay, so you can see for this particular curve, you know, the hump is slid out a lot more than the last one, because just that little bit right there, I had to go out to 29.707 just to have 1% to my left. I still have 99% to my right. Okay, so the degrees of freedom really does shift the shape of the curve. One more. So I guess I can rub this out. Okay, so read the next one while I erase this. Sample size 25, I want a two-tail probability of 0.02. So I say this one requires a little thought, not that much. So I have, you know, whatever my curve looks like. And its degrees of freedom is, the sample is 25. Yeah, so it's 25 minus 1 equals 24. And if I remember right, my table does have 24. Here, let me get rid of that for a second so you can see a little bit better. Okay, now I want a two-tail 0.02 probability. So what I need to do is, let's see, so two-tail 0.02 area. So I want 0.02 divided by 2 equals 0.01 area in each tail, don't I? I'm hitting the squeaking. Let's try this. Okay, so I want somewhere out here some value, so that's 0.01, and somewhere back here some value, so that's 0.01. So to get this one, I go into the table at degrees of freedom 24, and now I can go forward. Come on. It's not coming. Darn it. Okay, I'm about to give up. I'm about to give up. All right, sorry, I got to give up here. It isn't going. I don't know why, but if you go back, there was a while when I had that second page that didn't go all the way down, the second part of the chart. If you look, I had those two things circled. Over here, let's do this one first. Over here at degrees of freedom 24, you can backtrack and see that I had the right one circled. You can get, because like I said, for a while I had up the second part of that chart, which only had like about 2/3 of the screen covered. You can go back there and see, but I went down to degrees of freedom 24, and I went over to 0.01, and I got that number right there. If you go back and check, see where that thing is circled, and it was 42.98. And then to get this one, I, of course, need 0.99 area to the right, just like before, right? Because I just want to take 1 minus the 0.01. So when I do that, I get that one over there. If you backtrack to where you have just that 2/3 of a chart on the page, you'll see that that was 10.856. 10.856. Okay, so that's really pretty much all there is to it. You now know how to calculate the test statistic, and you know how to find critical values. And so, you know, you can do hypothesis testing now. We'll do some examples in the next lecture, but you should be able to see, yeah, I know exactly what I'm going to do. I'm going to calculate my test statistic. I'm going to see if, get this sort of a thing set up and see if it falls in the rejection region or not, and then I'm going to be able to make my conclusions, right? So you should just be able to do it, but I'll do like, I don't know, maybe 3 examples next lecture. All right, I'll stop there.